August 17, 1943. Under a full moon over the Baltic Sea, 596 RAF heavy bombers crossed into German airspace and struck the Peenemünde Rocket Research Center on Usedom Island. The raid shattered Germany's centralized wonder weapon program and delayed terror strikes that could have changed the course of the war. This wasn't just another Hydra Mark bombing mission. Operation the first time Allied forces deployed revolutionary electronic countermeasures that would redefine aerial warfare. The raid didn't merely destroy buildings and kill scientists. It forced Germany to abandon its efficient centralized rocket program, scattered irreplaceable expertise across sites, and validate dozens of hidden radar jamming techniques that would dominate electronic warfare for decades to come. Peenemünde represented the beating heart of Germany's most ambitious military technology program. Located on the remote Baltic island of Usedom, this sprawling complex housed the primary research and testing facilities for both the V-1 flying bomb and the revolutionary V-2 rocket. Here, under the direction of scientists including Werner von Braun and propulsion expert Dr. Walter Thiel, German engineers worked to perfect long-range weapons that could strike British cities from hundreds of miles away without warning. The strategic threat was unprecedented. Unlike conventional bombers that could be intercepted by fighters or brought down by anti-aircraft guns, the V-2 rocket traveled at supersonic speeds and arrived without any advance warning. These missiles could reach London from launch sites in occupied Europe, threatening invasion staging areas, vital ports, and supply lines that would prove crucial for any Allied assault on the continent. If Peenemunde's program reached full operational capacity, Britain's ability to serve as the launching point for European liberation would face catastrophic disruption. Intelligence gathering began in earnest during the summer of 1943. Allied reconnaissance flights over the Baltic photographed unusual installations that defied conventional military categorization. Aerial imagery analysts noted massive concrete test stands, elongated launch ramps, and heavy security measures that marked Peenemünde as something extraordinary. Prisoner interrogations yielded fragments of information about rocket experiments. Ultra-intercepts and traffic analysis revealed increased German communications activity centered on this remote island facility. Operation Crossbow, the comprehensive Allied effort targeting German V-weapon sites, identified Peenemünde as the primary hub requiring immediate action. Photographic interpreters studying reconnaissance images recognized test structures unlike anything in their experience. The concrete stands appeared designed for vertical launches. The rail network suggested movement of massive components. The residential areas housed what appeared to be a significant scientific community. Every indicator pointed to a weapons program that represented a fundamental shift in military technology. The urgency was undeniable. German development timelines suggested possible operational deployment by autumn 1943. If the V-weapon program achieved mass production capability before Allied invasion plans matured, the strategic balance could shift decisively in Germany's favor. Peenemünde had to be neutralized before it could unleash terror weapons against British cities and military installations. RAF Bomber Command approached Operation Hydra as a precision strike requiring their heaviest available force. The target demanded destruction of research facilities, test stands, assembly buildings, and critically the residential areas housing the scientific personnel whose expertise made the program possible. This wasn't area bombing designed to destroy industrial capacity through sheer tonnage. This was surgical warfare aimed at decapitating a specific technological threat. The force composition reflected the mission's importance. Approximately 324 Avro Lancasters formed the backbone of the attacking force, supported by 218 Handley Page Halifaxes and 54 short Stirlings. Nearly 600 heavy bombers represented one of the largest precision raids of the war, requiring coordination between multiple bomber groups and specialized Pathfinder squadrons. Electronic warfare measures transformed Operation Hydra into a technological experiment with strategic consequences. Operation Whitebait provided the deception element, launching a diversionary raid toward Berlin designed to draw German night fighters away from the actual target. RAF bombers employed H-2S ground mapping radar for navigation and target identification, while Pathfinder aircraft prepared to mark Peenemünde with flares for the main force. Mosquito aircraft carried jamming equipment to disrupt German radar networks. Most significantly, Operation Hydra marked the first operational deployment of Window, the British code name for chaff. These strips of aluminum foil, cut to specific lengths corresponding to German radar wavelengths, created false echoes that blinded defensive radar systems. The technology had been ready for months, but concerns about German retaliation against British cities had delayed its use. Peenemunde's importance finally justified revealing this revolutionary countermeasure. Operational planning required unprecedented precision. Air crews studied detailed models of Peenemünde constructed from reconnaissance photographs. Navigator training included memorization of Baltic Sea landmarks and approach routes. The full moon timing allowed visual target identification while providing enough darkness for bomber protection during the long flight over enemy territory. The risks were substantial. Deep penetration into German airspace without fighter escort, extended flight times over heavily defended territory, and concentrated anti-aircraft defenses around a high-priority target. The attack sequence followed a carefully orchestrated three-wave plan. Pathfinder aircraft would mark target areas with colored flares, enabling precision bombing despite nighttime conditions. The first wave concentrated on residential areas housing scientific personnel, recognizing that expertise was as valuable as equipment. The second wave targeted test stands and production facilities with blockbuster bombs and armor-piercing munitions designed to destroy reinforced concrete structures. The third wave finished remaining targets and struck hardened installations that required multiple hits. As the bombers approached Peenemünde, the electronic battle began in earnest. Window chaff created a blizzard of false returns on German radar screens, making it impossible to track individual aircraft or coordinate interceptions. Jamming equipment aboard escort Mosquitoes added additional interference. The diversionary raid toward Berlin successfully drew significant fighter strength away from the actual target area. German radar operators found themselves confronting a wall of electronic noise that rendered their sophisticated detection systems virtually useless. The bombing itself proceeded with devastating efficiency. Pathfinder flares illuminated the target complex, revealing the distinctive test stands and assembly buildings that intelligence had identified. Concentrated explosions walked across the research facilities, collapsing specialized laboratories and destroying irreplaceable equipment. The residential areas suffered particularly heavy damage, achieving the mission's goal of disrupting the human infrastructure supporting rocket development. Dr. Walter Thiel, one of Germany's leading rocket propulsion experts and a key figure in V-2 engine development, died during the raid along with several other senior scientists. The loss of such specialists represented a blow that could not be easily remedied. Rocket propulsion required years of specialized knowledge and experimental that individual experience engineers had accumulated through countless test firings and design iterations. Replacing dead scientists meant not just finding qualified personnel, but recreating the accumulated expertise that made Peenemunde's program so advanced. German defensive response intensified as the raid progressed. Local Luftwaffe flak and night fighter units engaged the bomber stream with increasing effectiveness as the electronic countermeasures lost their initial surprise advantage. Searchlights probed the darkness, occasionally illuminating bombers for anti-aircraft gunners. Night fighters that had avoided the Berlin diversion began arriving over Peenemünde, intercepting bombers during their withdrawal. The human cost reflected the mission's strategic importance and the strength of German defenses. Approximately 40 to 41 bombers were lost during the operation, representing roughly 7% of the attacking force. Over 200 aircrew paid with their lives were wounded or faced capture and imprisonment. Each lost bomber represented 7 highly trained men whose replacement required months of specialized instruction. The price was steep, but the strategic calculations demanded acceptance of such losses to prevent potentially catastrophic damage to British cities and invasion preparations. Physical damage at Peenemünde exceeded expectations. Test stands collapsed under direct hits from armor-piercing bombs. Assembly buildings burned throughout the night. Storage facilities containing completed rockets and specialized components suffered direct hits. Machine tools and precision instruments required for rocket manufacture lay buried under rubble or destroyed by blast effects. The fires continued burning for days, consuming technical documentation and prototype components that represented years of development work. The human impact extended beyond immediate casualties. Several senior scientists requested transfers to safer locations. Others were relocated by German authorities concerned about losing additional expertise to future raids. The concentration of talent that had made Peenemünde so effective began dispersing across multiple sites, reducing efficiency and hampering the collaborative research that had driven rapid progress in rocket technology. But the psychological damage ran deeper than physical destruction. The concentration of Germany's finest rocket engineers within Peenemunde's secure compound had created an intellectual ecosystem where expertise cross-pollinated daily. Scientists working on guidance systems collaborated with propulsion specialists who shared insights with structural engineers. This collaborative environment accelerated problem-solving and innovation in ways that formal organizational charts could never capture. The raid shattered this delicate network of human relationships and technical knowledge sharing. German authorities recognized immediately that Peenemünde could never again serve as the centralized hub for rocket development. The facility's location on a Baltic island, while providing security from ground attack, made it vulnerable to future air raids that German air defenses could not reliably prevent. Within weeks of the August attack, orders went out to disperse the V-weapon program across multiple sites throughout occupied Europe and the German Reich itself. The dispersal process created logistical nightmares that would plague German rocket production for the remainder of the war. Critical components that had been manufactured in adjacent buildings at Peenemünde now came from facilities hundreds of miles apart. Quality control procedures that relied on face-to-face coordination between engineers became impossible when those engineers worked at different sites. Technical documentation that had been centralized in Peenemunde's archives was copied and distributed, but inevitably some information was lost or corrupted in transit. Underground production facilities began sprouting across Germany as authorities sought bomb-proof alternatives to exposed surface installations. The most notorious of these became Mittelbau Dora, a subterranean factory complex carved into the Harz Mountains near Nordhausen. Here, thousands of concentration camp prisoners labored under horrific conditions to assemble V-2 rockets using components shipped from scattered production sites. The underground environment created new technical challenges as humidity affected precision instruments and transportation difficulties delayed component deliveries. The human cost of dispersal extended beyond the immediate casualties at Peenemünde. Rocket scientists and technicians found themselves separated from colleagues who had worked alongside them for years. Research teams that had developed innovative solutions through informal collaboration were broken up and reassigned to different facilities. The institutional memory that made Peenemünde so effective began fragmenting as specialists adapted to new environments and different organizational structures. Production quality suffered immediately. Rockets assembled at dispersed facilities using components from multiple suppliers experienced higher failure rates than those built at Peenemünde. Quality control inspectors who had learned to identify potential problems through years of experience at the central facility could not transfer that knowledge effectively production to new lines operated by INEC's new facility, experienced workers. Each had to develop its own procedures and learn from its own mistakes, processes that consumed valuable time and resources. Meanwhile, Allied intelligence officers studying reconnaissance photographs and intercepted communications began recognizing the strategic impact of Operation Hydra. German radio traffic patterns indicated increased coordination difficulties between rocket production sites. Photographic analysis revealed construction activity at multiple new facilities, suggesting the dispersal that Allied planners had hoped to achieve. Prisoner interrogations confirmed that German rocket engineers were expressing frustration with production delays and coordination of electronic problems. The validation countermeasures during the Peenemünde raid transformed Allied bombing doctrine across all theaters. Window chaff, which had been held in reserve for months due to fears of German retaliation, proved so effective that it became standard equipment for all major bombing operations. The techniques developed for jamming German radar were refined and expanded, leading to increasingly sophisticated electronic warfare capabilities that gave Allied bombers significant advantages in penetrating enemy airspace. German radar operators found themselves confronting a new reality where their sophisticated detection systems could be rendered ineffective by strips of aluminum foil and coordinated jamming signals. The Würzburg radar installations that had provided early warning and fire control guidance for anti-aircraft batteries struggled to distinguish between genuine aircraft and the clouds of false returns created by window chaff. Night fighter crews who had relied on radar guidance to intercept bomber formations discovered that their targeting systems were overwhelmed by electronic interference. The technical lessons learned during Operation Hydra influenced subsequent Allied operations throughout 1943 and 1944. The combination of diversionary raids, pathfinder target marking, and electronic countermeasures became the standard approach for major bombing missions against high-priority targets. RAF Bomber Command incorporated these techniques into training programs, ensuring that aircrew understood both the capabilities and limitations of their electronic warfare tools. German defensive measures evolved in response to these new Allied tactics, but always remained one step behind. Luftwaffe technicians developed improved radar frequencies and signal processing techniques designed to counter window chaff, only to discover that Allied intelligence quickly identified these modifications and developed new countermeasures. The electronic warfare battle became an escalating cycle of measure and countermeasure that consumed increasingly scarce German technical resources. The delay in V-weapon deployment proved more significant than initial assessments suggested. German planning documents captured after the war revealed that rocket attacks against British invasion staging areas had been scheduled for late 1943, potentially disrupting Allied preparations for the cross-channel assault. The dispersal forced by the Peenemünde raid pushed operational deployment back by months, allowing Allied invasion plans to mature without the threat of supersonic terror weapons striking ports, airfields, and troop concentrations. When V-2 attacks against British targets finally began in September 1944, they came too late to affect Allied invasion preparations and at reduced intensity compared to original German projections. The rockets that fell on London and Antwerp represented the product of a fragmented, inefficient production system operating under constant resource constraints. While these attacks caused significant casualties and maintained psychological pressure on Allied populations, they never achieved the strategic impact that a fully operational Peenemünde program might have delivered months earlier. The ripple effects of the August 1943 raid continued expanding throughout the German war economy. Resources that had been concentrated at Peenemünde were now scattered across dozens of facilities, each requiring its own security measures, transportation networks, and administrative overhead. The efficient production lines that had characterized the centralized program gave way to complex supply chains vulnerable to bombing, sabotage, and simple coordination failures. Transportation became a critical bottleneck as components manufactured at different sites required coordination and delivery to final assembly points. German railways, already strained by military transportation demands and Allied bombing campaigns, struggled to maintain reliable delivery schedules for rocket components. Trucks diverted from other military uses carried precision instruments and guidance systems along increasingly dangerous roads, subject to air attack and partisan activity. The decentralized production system that emerged from Peenemunde's ruins created cascading inefficiencies that German planners had never anticipated. Specialized components that once moved between adjacent workshops now required rail transport across hundreds of miles of increasingly dangerous territory. A guidance gyroscope manufactured in Bavaria needed coordination with propulsion systems built in Thuringia and warheads assembled in underground factories carved from mountain rock. Each connection point introduced delays, quality control problems, and vulnerability to Allied interdiction. Underground facilities presented their own technological nightmares. The Mittelbau Dora complex, hewn from Harz Mountain limestone by slave labor, suffered from humidity that corroded precision instruments and temperature fluctuations that affected delicate calibration procedures. Rockets assembled in these subterranean chambers experienced failure rates dramatically built higher than those in Peenemunde's controlled environment. Components that had functioned perfectly in surface facilities malfunctioned when exposed to the underground conditions that German engineers had not fully considered during their hasty dispersal planning. The human cost of dispersal extended far beyond the immediate casualties at Peenemünde. Rocket scientists found themselves isolated from colleagues who had worked alongside them for years, separated by security restrictions and geographic distances that made collaboration nearly impossible. Research teams that had developed innovative solutions through informal daily interaction were broken apart and reassigned to different facilities, hundreds of miles apart. The institutional memory that had made Peenemünde so effective began fragmenting as specialists adapted to new environments, different organizational structures, and unfamiliar support personnel. Production schedules that had operated with clockwork precision at the centralized facility collapsed under the coordination demands of dispersed manufacturing. Quality control inspectors who had learned to identify potential problems through years of experience at Peenemünde could not transfer that knowledge effectively to new production lines operated by inexperienced workers recruited from other industries. Each new facility had to develop its own procedures, learn from its own mistakes, and establish quality standards through trial and error processes that consumed precious time and increasingly scarce resources. Meanwhile, Allied intelligence officers studying reconnaissance photographs and intercepted communications began recognizing the strategic impact of Operation Hydra. German radio traffic patterns indicated increased coordination difficulties between rocket production sites scattered across occupied Europe. Photographic analysis revealed construction activity at multiple new facilities, suggesting the dispersal that Allied planners had hoped to achieve. Prisoner interrogations confirmed that German rocket engineers were expressing mounting frustration with production delays, coordination problems, and quality control issues that had been virtually unknown at Peenemünde. The validation of electronic countermeasures during the Peenemünde raid transformed Allied bombing doctrine across all theaters of operation. Window chaff, which had been held in reserve for months due to fears of German retaliation against British cities, proved so devastatingly effective that it became standard equipment for all major bombing operations. The techniques developed for jamming German radar networks were refined and expanded, leading to increasingly warfare capabilities sophisticated electronic that gave Allied bombers significant advantages in penetrating enemy airspace throughout the remainder of the war. German radar operators found themselves confronting a new reality where their sophisticated detection systems could be rendered ineffective by simple strips of aluminum foil and coordinated jamming signals. The Würzburg radar installations that had provided early warning and fire control guidance for anti-aircraft batteries struggled to distinguish between genuine aircraft signatures and the clouds of false returns created by window chaff. Night fighter crews who had relied on radar guidance to intercept bomber formations discovered that their targeting systems were overwhelmed by electronic interference that made accurate interception nearly impossible. The technical lessons learned during Operation Hydra influenced subsequent Allied operations throughout late 1943 and into 1944. The combination of diversionary raids, pathfinder target marking, and coordinated electronic countermeasures became the standard approach for major bombing missions against high-priority targets deep within German-controlled territory. RAF Bomber Command incorporated these techniques into comprehensive training programs, ensuring that aircrew understood both the capabilities and limitations of their electronic warfare tools while maintaining operational security about the most sensitive countermeasures. German defensive measures evolved in response to these new Allied tactics, but remained consistently one step behind technological developments. Luftwaffe technicians developed improved radar frequencies and signal processing techniques specifically designed to counter window chaff, only to discover that Allied intelligence services quickly identified these modifications and developed new countermeasures. The electronic warfare battle became an escalating cycle of measure and countermeasure that consumed increasingly scarce German technical resources and diverted scientific talent from offensive weapons development to defensive systems. The delay in V-weapon deployment proved far more strategically significant than initial Allied assessments had suggested. German planning documents captured after the war revealed that coordinated rocket attacks against British invasion staging areas had been scheduled for late autumn 1943, potentially disrupting Allied preparations for the cross-channel assault that would become Operation Overlord. The dispersal forced by the Peenemünde raid pushed operational deployment back by crucial months, allowing Allied invasion plans to mature without the constant threat of supersonic terror weapons striking the ports, airfields, and troop concentrations that would prove essential for European liberation. When V-2 attacks against British targets finally commenced in September 1944, they arrived too late to affect Allied invasion preparations and at significantly reduced intensity compared to original German projections. The rockets that fell on London, Antwerp, and other Allied-controlled cities represented the product of a fragmented, inefficient production system operating under constant resource constraints and coordination difficulties. While these attacks caused significant civilian casualties and maintained psychological pressure on Allied populations, they never achieved the strategic impact that a fully operational, centralized Peenemünde program might have delivered months earlier during the critical invasion planning period. The ripple effects of the August 1943 raid continued expanding throughout the German war economy as resources that had been efficiently concentrated at Peenemünde were now scattered across dozens of facilities, each requiring its own security measures, transportation networks, and administrative overhead. The streamlined production lines that had characterized the centralized program gave way to complex supply chains vulnerable to Allied bombing campaigns, partisan sabotage activities, and simple coordination failures that multiplied as the transportation network deteriorated under wartime pressures. Transportation bottlenecks became critical limiting factors as precision components manufactured at different sites required careful coordination and reliable delivery to final assembly points. German railways, already strained beyond capacity by military transportation, demands, and systematic Allied bombing campaigns against marshalling yards and rail infrastructure, struggled to maintain predictable delivery schedules for delicate rocket components that required specialized handling procedures. Military trucks diverted from other essential duties carried precision instruments and guidance systems along increasingly dangerous roads, subject to constant air attack and growing partisan activity in occupied territories. The psychological impact on German rocket personnel proved as damaging as the physical destruction of a facility's equipment. Scientists and technicians who had worked in Peenemunde's collaborative environment found themselves isolated in underground bunkers or remote facilities where security restrictions prevented the informal knowledge sharing that had driven rapid innovation. Morale declined as working conditions deteriorated, and the prospect of German victory grew increasingly remote. Some specialists requested transfers to less critical programs, while others were forcibly relocated by authorities concerned about concentrating irreplaceable expertise in vulnerable locations. By early 1944, the dispersed V-weapon program bore little resemblance to the efficient, centralized operation that had existed at Peenemünde before Operation Hydra. Production rates lagged behind original projections, quality control problems multiplied, and coordination difficulties created delays that pushed operational deployment further into the future. The wonder weapon that was supposed to change the strategic balance of the war had become resources a logistical nightmare consuming without delivering proportional results. Operation Hydra didn't end German rocketry, but it accomplished something far more devastating. By shattering the efficient centralized program at Peenemünde and forcing dispersal across dozens of vulnerable sites, the raid transformed Germany's wonder weapon dream into a logistical nightmare. The rockets that finally fell on London and Antwerp in September 1944 arrived 13 months later than German planners had originally intended, too late to disrupt Allied invasion preparations and at far lower intensity than a fully operational Peenemünde program might have achieved. The electronic warfare techniques validated over the Baltic that August night revolutionized aerial combat for the remainder of the war. Window chaff and coordinated jamming became standard equipment for every major Allied bombing operation, while the lessons learned about radar countermeasures influenced military doctrine for decades to come. German defensive systems never fully recovered from the technological surprise that rendered their sophisticated detection networks virtually blind when they needed them most. The human cost was undeniable. Over 200 Allied aircrew paid with their lives or freedom for those crucial months of delay. German scientists and workers at Peenemünde, including civilians in the residential areas, suffered casualties that cannot be forgotten. Yet the strategic arithmetic proved grimly decisive. The raid bought the Allies time to complete invasion preparations without the constant threat of supersonic terror weapons striking British ports and staging areas. In the end, Operation Hydra demonstrated that even the most advanced technology remains vulnerable to coordinated attack at the right moment. A single night's work by 596 bombers, supported by strips of aluminum foil and coordinated deception, neutralized what might have been Germany's most strategically significant weapon. The Wonder Weapon met its match not in superior German engineering, but in Allied intelligence, electronic warfare innovation, and the courage of airmen who flew through the night to strike at the heart of Nazi technological ambition.